Now we'll discuss some agent types. The first one is the table-driven agent, which use a percept sequence and action table in memory to find the next action. They are implemented by a large lookup table. So you can consider if there are millions and billions of percept sequences every millisecond for an automated driving vehicle and corresponding actions, this kind of table will be so large that it will not be practical to store in any kind of computer memory. So table-driven agents for large action tasks are almost impossible. The next one is a simple reflex agent. A simple reflex agent acts only on what it sees right now. No memory, no planning. An example will be our vacuum world. If the square is dirty, suck. If it's clean, move. That's it. In real life, think about driving. If the car ahead brakes, you brake. You live in the moment. These agents are fast and simple, but limited. They only work well in fully observable environment. If something is hidden or unclear, that means partially observable, they can get stuck or make mistakes, like confusing a brake light for a turn signal. Sometimes we add a little randomness to avoid infinite loops, like doing the same action over and over. We can add some kind of randomness. So simple reflex agents are quick, rule-based, but not very smart. Then comes the agents with memory, also sometimes called the model-based reflex agent. This kind of agents have some internal state which is used to keep track of past states of the world. Not a lot of past states, but maybe a very little bit of it. When environments are only partially observable, reflex agents that rely solely on the current percept are not enough. To overcome this, agents maintain an internal state, a memory of past percepts that helps them infer what they cannot directly see right now. This requires a model of the world, knowledge about how the environment changes on its own and how the agent's actions affect it. For example, if a car was behind you a moment ago, you can reasonably expect it to still be nearby. And if you turn the steering wheel right, you expect the car to move right. A model-based reflex agent combines new percepts with its internal state, updating its best guess of the current situation. While this state is rarely perfect, it allows the agent to make informed decisions in uncertain settings, like a taxi deciding to refuel on the way home, based on both where it is and where it intends to go, or what it intends to do. The next one is goal-based agents or agents with goals. Sometimes just knowing the current state isn't enough. Imagine a taxi at an intersection. It can go left, right, or straight. The right choice depends on the goal, like reaching the passenger's destination. A goal-based agent uses both the model of the world and the goal to choose actions. For example, if the car in front brakes, the agent reasons, to avoid a crash, I must also brake. So that's the goal, which drives an action. So we have all the models diagram ready, and feel free to look at them. And here the condition action rules, and for goal-based agent, these are the goals which kind of guides what action I should do now. And so basically the power of goal-based agent is flexibility. If the goal changes, say the passenger wants a new destination, the agent can simply update the goal and adjust its behavior. Reflex agents, by contrast, would need many rules rewritten, if the suddenly in the middle of the trip the passenger changes its goal. Goal-based agents also consider the future. What will happen if I take this action? Will it bring me close to my goal? Like what my actions do, that's important, okay? Considering the future. That's where search and planning in AI comes into play. The last one is utility-based agent. And the key idea is goal alone are not enough. For example, a taxi agent might reach its destination using many different routes. All of them satisfy the goal of reaching to your destination, but some are faster, safer, cheaper, or more reliable. A simple goal test cannot capture these differences. That's where the utility comes in. In AI, utility is a numerical measure of how desirable a state is for the agent. Goals are binary, success or failure. Utilities, on the other hand, provide degrees of desirability, how happy it will make you. An agent's utility function internalizes its performance measures. If the utility function aligns well with the external performance measure, then maximizing utility leads to rational behavior. This helps in two situations. One is when there is a conflicting goal, and the second when there is an uncertainty. Let's consider the conflicting goal. Example, a speed versus safety thing. The utility function balances the trade-off. That how fast you should go and still make sure the drive is safe, feels safe. And the other is uncertainty. When success isn't guaranteed, the agent picks the action with the highest expected utility or average outcome, considering probabilities. So a utility-based agent chooses action to maximize its expected utility. This makes it more flexible than simple reflex or goal-based agents, but it's also harder to build since the agent must model the environment and compute outcomes efficiently.